Welcome to Quantum Curious, and in today's video, I'm going to start a new series that is the problem solving series. So in this series, we will going to solve some problems through some past papers of interest of PhD, MPhil, and MSc of various universities of Pakistan. So today I have chosen a past paper of 2018 spring admission of MPhil and PhD admission in Quaid-e-Azam University. So for those who belong to Pakistan knows that Quaid-e-Azam University is one of the top university of Pakistan and also uh, one of the best physics department in Pakistan. And also it is also a well-known university around the globe. So, so let's start with the first question, and first question is related to the mechanics. So the question is that a block of mass m on a horizontal surface is attached to a spring having spring constant k. We pull the mass a distance x to the right of x is equal to 0, which is the equilibrium position, and let it go. How far the left how far to the left of the equilibrium position x is equal to 0 will it reach? Assume that the kinetic coefficient of friction between the mass and the surface is mu k. So here we are given some information about a mass that is attached to a spring, and the mass is placed horizontally and it is resting on a surface having a kinetic coefficient of kinetic friction mu k. And we are going to displace this block of mass m to the right of equilibrium position, and the displaced distance or displacement would be a. So our goal is to find the distance that the block is going to travel to the left of the equilibrium position. So here I have solved this problem. So we have initially this uh, scenario where the block is at equilibrium position, and we are going to apply some force and going to displace it from the equilibrium position to the position x is equal to a, that is present at right of the equilibrium position. So our goal is to find that quantity x, that is a capital X, to the left of the equilibrium position. So you can see that in both cases, the velocity of at the point A and at the point X that we are going to calculate would be zero. And in the meanwhile, the kinetic friction, the kinetic force will be doing a negative work to the block. So we can do uh, multiple techniques to solve this problem, but the easiest one would be to use the energy uh, theorem, or you can say conservation of energy. So first we have to find the work done by kinetic friction force, and that is, first we are going to find the kinetic friction, uh, and we know that it is proportional to the normal force acting on the body of mass m. And we know that normal force and the gravitational force uh, are going to cancel each other because there is no movement uh, in the vertical direction. So normal force is equal to mg. So we are going to plug it in that equation. So the four kinetic friction have the form mu k mg. So potential energy at x is equal to a, that is the initial position we have, uh, should be 1 over 2 k a square, and the kinetic energy at that point should be zero because the block is resting at that position. On the other hand, the potential energy at the far left of the equilibrium position should be 1 over 2 kx square, and we have to find that uh, value of displacement. And again, the kinetic energy at that point should be equal to zero because block is going to stop at the moment at this moment when he's going to reach the farthest point at the left of the equilibrium position. And the work done by the kinetic friction should be addition of the two works, that is the work done by kinetic friction from x a to x 0, then x 0 to x that we are going to find. So we have work done by the kinetic friction is given as this. So again, using uh, conservation of energy, uh, first we put these value of the potential energy and work done by friction, and then work done by then the potential energy at the point that we want to find. So going through algebra, we can easily find that value. So you can see that there is no option like that we have found here. But we know that we are using some coordinate system that have a positive direction towards the right. So the negative direction uh, towards the left should have a negative sign for the position at the equilibrium position to the left of that to the equilibrium point. So adding negative sign towards this equation, we are going to get that answer. So we can see that the correct answer is choice E in that case. So it is given here. So the answer of this problem is the last option. So the next question is again from mechanics, and it is using the concept of the collision. So a completely inelastic collision occurs between a mass m1 moving upward with velocity v1 and a mass m2 moving downward at velocity v2. How does the combined mass rise above the point of collision? The collision occurs close to the surface of Earth. Ignore air resistance. So the information given in that problem is that the two uh, masses of m1 and m2 are going to have an inelastic collision, and in inelastic collision the two masses are going to combine to each other and they will move then further. So uh, we can solve it by using the concept of the conservation of momentum and some other equation of kinematics. So consider here a scenario that is uh, this is a floor or surface of Earth, and the mass m1 is moving upward with velocity v1, and mass m2 is moving downward with velocity v2, and they are uh, moving under the force of gravity. So we want to know the height uh, on that these two combined masses are going to achieve after the collision. So first we will apply the moment, the uh, conservation of momentum. So we know that m1 v1 minus m2 v2, and negative sign is due to that the then the velocity of direction of the mass m2 is downward, and we have said that the coordinate system as such that the the y-axis is upward. So the positive direction is upward. So if the velocity is downward, so it should have negative sign. So due to the inelastic collision, uh, the the masses of the two bodies are going to combine after the collision, and they will move with velocity vf. So here we can find uh, one of the quantity that is of our interest, that is the final velocity of the combined masses. So again, we can use uh, the energy conservation principle. So the kinetic energy of the masses after the collision is given as this, and the potential energy that is these masses are going to achieve after moving some certain height h is given as this equation. So cutting out all these things, and we could see that uh, the height that they are going to achieve after having collision, that is the inelastic collision, is going to be this. So none of the answer is given in this that we have found, but I think there is some kind of mistake here, because if we do some dimensional analysis, there should be squared in the solution of the problem. So answer, I think A is quite close to it. So we are going to consider this in that case, because I think I have made some mistake here. There is 1 over 2, and that should be not here. So answer 2 should be uh, 1 over 2g, and uh, there should be 1 over 2g factor, uh, and there should be some square of this quantity. So answer is very close to this A, so we are going to consider it as the correct one. So another question is from again mechanics, and the question is that the question says that a girl of mass m stands on the rim of a frictionless merry-go-round of radius r and rotational inertia I that is not moving. She throws a rock of mass m horizontally in a direction that is tangent to the outer edge of the merry-go-round. The speed of the rock relative to the ground is v. Afterwards, what is the angular speed of the merry-go-round? So here again, we could see that we are given with some bunch of information, that is, we have a merry-go-round, and a girl is standing on the top of the merry-go-round, and standing on the rim, and initially the merry-go-round is not moving, and it has some rotational inertia, that is I, and then at some instant the girl throws a rock of mass m, and the velocity of the rock relative to the ground is tangent to along the tangent to the radius of the or you can say along the to the curved surface, tangent to the curved surface of the rim of the merry-go-round, and we want to know that what would be the angular speed after this situation, because we could assume, or we could imagine that uh, the merry-go-round would be uh, circulating after that, uh, or rotating after that situation. So here we have the initial scenario where girl is standing having mass m on a rim of the merry-go-round, and she throws a rock of mass m with velocity v. So how can we solve this problem? So we could see that uh, from the symmetry of the problem, we can use the conservation of angular momentum here, and we could easily found the angular uh, velocity after that. So angular momentum initially has value of 0 because there is no rotation around any kind of origin. And angular momentum after, that is the final angular momentum after the girl throws the rock horizontally, we could see that the angular momentum should be a addition of two quantities, that is the angular momentum of the rock and the angular momentum of the merry-go-round. So angular momentum of the rock has negative value because we are assuming that the positive value is is going to be along the right direction. So it is minus MVR, and or you could assume that by taking some kind of coordinate axis to calculate the angular momentum of the rock uh, with respect to the origin of this merry-go-round. And angular momentum of the merry-go-round is this quantity, where mr square comes from the factor that the mass m, that is the mass of the girl, is along the rim and have some distance r, that is the radius of the merry-go-round uh, from the origin. So again, we can use conservation of angular momentum in that case and can easily find the answer. So in that case, the answer is going to be C, and that is the right answer of this problem. So the next question, that is the fourth question, is from the electrostatics. So the question is that a spherical charge distribution has charge density rho that is constant from r is equal to 0 to r is equal to r, capital R, and 0 beyond. What is the electric field for all values of r less than r? So we are given with some kind of sphere, and we want to know the electric field inside the sphere, and we are given with the constant charge density. So in that case, we can find electric field inside the sphere by use of the Gauss's law. So we can use Gauss's law to calculate the electric field inside the spherical surface or spherical ball. And the Gaussian surface we are going to consider is also spherical with radius r, small r, and the small r is it's smaller than the radius of the whole sphere. So first we want to know what is the charge enclosed by this Gaussian surface. So we can see that we can calculate by using the charge density and the volume, and we know that the volume of the sphere or with radius small r would be 4 by 3 pi r cube. So again, using Gauss's law, we know that the electric field and is constant, so we can take it out of integral, and the area of the sphere is 4 pi r square, uh, and putting the value of the charge enclosed in that equation, we can easily find the electric field, or in that case. So we can see that electric field in that case is increasing linearly because of the factor of R inside the charged sphere. So the answer here in that case is A. So the next question is about magnetic force, and there is some kind of mistake in the statement. So find the direction of the magnetic field acting on a positively charged particle moving in the direction which is into the page as shown in this figure, the direction of the magnetic force acting on it. So there's kind of contradiction in that statement because we are given with magnetic force and its direction, and we are given with a velocity. So uh, we have to find the magnetic direction of the magnetic field. So we can find it by using the formula of the charge of the force on the magnetic force on the charge with some velocity v. So here is the formula v cross p q is equal to fp. So we are given with the direction of the magnetic force and the velocity. So we can set up this problem by introducing the coordinate system. So here we are using coordinate system with z-axis into the page and y-axis upward and x-axis uh, horizontally to the right. So in order to be magnetic force, sorry, in order to be magnetic force negative along the horizontal axis, that is the x-axis, the magnetic force we could see that should be upward in order to make this cross product negative. So in that case, the answer is that the magnetic force would be would have direction upward. We could also solve it by the right hand rule, and instead of using this formula, but the people who are more mathematically inclined, they can use this kind of formula every time. So again, the next question is again from electromagnetism, and it is quite interesting one. So a sphere of radius r surrounds a particle with charge q located at its center in the figure. The electric field through a circular cap of half angle theta is. So we are given with a sphere and it is enclosing a charge q and it is present at the origin and the surf and this sphere has radius r, and we want to find the electric field passing through this cap. So it is very easy to find the electric field passing through the whole sphere, but uh, in that case, it is not that easy to find the spherical to find the electric flux. Sorry, to passing through the surface of some area A and forming some angle from the origin. So first, we have to find that area enclosed by the surface, and then we can easily find the electric flux or passing through that gap. So we know that electric flux is just E dot dA, where dA is some area, and we want to find that. So from spherical coordinates, we can find the differential area of the sphere by this formula, and we know that phi should be 0 to 2 pi because it's the azimuthal angle, and theta has some restrictions because it is not going from 0 to pi. So we have to restrict the theta in that case. So it is from 0 to theta, and then we can easily find the area enclosed by this cap. So finding the area, and we know that electric field of produced by this charge has value q over 4 pi epsilon naught r square, and canceling out some common terms, we can easily find the electric flux passing through that cap. So in that case, the right answer is D, and it makes some physical sense. Okay, so the next question is that the expression for free energy of a system connected to a heat bath at temperature T and with two non-degenerate states, one at energy zero and other at epsilon. So it is from statistical mechanics. So we can easily find by finding the partition function of the given system. So we can find the partition function of the given system uh, at equilibrium with heat bath of temperature T, and we know that the free energy has this form. So putting the partition function in that scenario, in that expression, we could find easily the free energy, and it has uh, answer A. So answer the option A is correct one. So an adiabatic expansion of an ideal gas is described by the expression this, where um, gamma and C are constants. The work done by the gas in expanding from this value of pressure and volume to this value of pressure and volume. So we want to find the work during the expansion of the gas. So we know that in adiabatic expansion there is no addition or emission of heat. So or you can say there should be no entry of heat. So in that case, Q is equal to zero, and we know that the change in uh, change in internal energy is directly proportional to the temperature. And using the first law of thermodynamics, we could see that the internal energy should be equal to the work done. So using the ideal gas equation, in that case, P is equal to nRT, we can put P1 and V1 in place of T1 and T2. So we are having this form. So in order to further simplify this, CV is equal to R, where R is the ideal gas constant, we can use the expression Cp minus Cv is equal to R, where gamma is equal to Cp or Cv, because we have to find the answer in terms of the gamma. So simplifying this result and using the expression from gamma, we could find the Cv or Cr quite easily, and the final answer is this. So in that case, the answer is going to be lambda minus 1 in the denominator. So answer should be this quantity, because in that case where P1 and V1 are have positive sign, but in that case it has a negative sign. So if we take the common and common subtraction or minus sign in that expression, we can make it as this. So here answer C is the correct one. So this is the last question we are going to see, and in the next video, we will solve this completely, or we'll solve more problems. So if we consider the spin of an electron, the maximal occupation number of an energy level in an ideal electron gas is. So we found to find maximal occupation number of energy level. So we know that if we only considering spin, so spin could be spin half, or uh, spin half the value of spin half, and it could be spin up or spin down. So maximal occupation number of energy should be, in that case, should be equal to 2. So this is the right this is the right option in that case. So we have solved quite a bit of number of problems related to mechanics, electromagnetism, and thermodynamics, and statistical mechanics. So you can imagine that, or you can see that the problems relating to mechanics were a bit hard, and then uh, the problems related to electricity and magnetism were not that hard instead uh, of that one. And the problems related to thermal physics and statistical mechanics were quite easy. So in the next video, I will go further deep into the problems of quantum mechanics and again some mathematical methods.